Now that we understand that stability is what we are after, let's build the necessary theoretical tools to explore it. This brings us to the restricted isometry property, a concept that was introduced by Immanuel Candes and Terence Tao in 2005. Let's recall how we have proven the uniqueness in the P0 case, with the hope that we could borrow some insights. X0 is an S-sparse vector, and we use it to create the vector B as A times X0. Thus, when solving the P0 problem, the solution x hat must obey the linear system Ax equals B, and it must also be, at most, S-sparse. The first of these two properties implies that the difference vector X0 minus X hat must be in the null space of A. Recall the definition of the spark, being the minimal possible number of non-zeros in vectors that are in the null space of A. Thus, the L0 norm of X0 minus X hat is lower bounded by the spark. We have already seen that we can lower bound the spark using the mutual coherence. From the other direction, I remind you that the L0 norm obeys the triangle inequality, and thus we get to this final outcome. Therefore, if S is below 1/2 of 1 plus 1 over mu, we necessarily get that X hat must be equal to X0, and this is the uniqueness result. Now let's try imitating this for our new case of P0 epsilon. X0 is as sparse as before, and we create the vector B by A times X0 plus a noise vector of epsilon bounded norm. When we solve the P0 epsilon, we get a solution X hat, and it should satisfy two properties. First, it must obey the constraint, and second, it must have no more than S non-zeros. Here is an attempt to describe the relation between X0 and X hat. Both Ax0 and Ax hat are at most epsilon away from B. Therefore, the distance between them is at most 2 epsilon. Also, the difference vector X hat minus X0 is 2s sparse at most. As the two last statements resemble those we got for P0, we should wonder if we could proceed in the same way using the spark. We are given these two properties we have just derived. Could we use the spark to handle this non-zero epsilon case? Unfortunately, the answer is negative. We must generalize the spark to handle the case where AZ is no longer 0, but of small norm value. So how do we generalize the spark for this case? Here is a different way to understand the spark that could help. Given the matrix A, we could build the submatrix AS by extracting S columns from A. Recall that A has M columns, and thus there are M choose S possibilities of constructing such submatrices AS. If the spark of A is known to be S, this implies that at least one of those AS's will have linearly dependent columns. Put differently, in this case, at least one of those AS submatrices will have a 0 as its smallest singular value. We will now leverage this behavior. Following the same construction, we consider again all the submatrices AS. We generalize the spark by allowing the smallest singular value to have a non-zero value. Indeed, being small, this means that the columns in AS are close to being linearly dependent. Put formally, we require that for all the AS submatrices, their smallest singular value is lower bounded by sigma min. Or equivalently, we require that for all vectors z of length s, the norm of AS times z divided by the norm of z is bounded from below by sigma min. As we will shortly see, in this statement we have characterized the matrix A with respect to supports of cardinality S. What if A is a unitary matrix? In this case, all its submatrices AS have S orthogonal columns, and sigma min is simply 1. As we will shortly see, we will refer to this case as the ideal situation. Indeed, inspired by the above, we replace sigma min squared by 1 minus delta S to emphasize the deviation of sigma min from 1. Written differently by rearranging this expression, we bound the L2 norm of AS times Z from below as shown here. The expression we have just written stands as a requirement on the matrix A. It states that for all z vectors of length s, the norm of as times z must be bounded from below by a value not far from the norm of z itself. Delta s quantifies this length deviation. Note that this requirement is demanded on all possible as created from A. If delta s is very small, this means that when multiplying those vectors by as, their length is hardly shrinked. We symmetrize this definition by adding an upper bound on the norm modification, being 1 plus delta s times the norm of z squared. This is the RIP, the restricted isometry property. It says that all submatrices AS behave nearly like orthogonal matrices in the sense that they do not modify much the length of Z. We now make this definition precise. For a given matrix A and for a chosen cardinality S, we define the RIP as the smallest possible value delta S that satisfies the near isometry property for all possible submatrices AS and all vectors Z. The smaller delta S, the better behaved the matrix A is. An alternative definition, and perhaps a clearer one for our needs, is this. We consider all the sparse vectors X of length m that have S non-zeros and pose the requirement on them. Thus, it is the complete matrix A that multiplies these vectors. Every such multiplication is effectively the same as AS times a vector of the non-zeros in X. This way, we avoid the need to speak about the sweep over all the AS possibilities. The implication of this definition is that A is well behaved if, when operating on S sparse vectors, it acts as a nearly orthogonal matrix. This is the RIP, and as we will shortly see, it is extremely valuable for our later analysis.